Okay, so we're going to be talking about all these different subjects in pharmacodynamics. Quickly, receptor theory, which I think you're getting quite a lot of in medchem. The dose-response relationship, potency, therapeutic index, and drug interactions. So quickly to talk about the drug receptor theory, this is going to be very rudimentary because I think this is not my area of expertise. It is the pharmacologist, so I'm sure Dr. Rao and Dr. Koopsey are going over this in 380. So the drug receptor interaction is where the component of a cell in which a drug interacts to produce a pharmacological effect. And we often say that it's a lock and key kind of action, so you can think of that metaphor. These can occur with both endogenous and exogenous compounds. So it could be a drug that we give, or it could be an endogenous compound that acts in this way. So just like this drug molecule comes in and turns on a receptor or blocks a receptor, you can have competition. We're probably very aware of this now. You can have competition for a receptor, and which compound is going to be the preferred compound to interact with the receptor is going to be dependent upon the affinity. High affinity will bind readily to the receptor even if the drug is in low concentration. Low affinity usually requires a higher drug concentration. This is all about Km, just like Michaelis-Menten, right? The efficacy is going to be the ability to stimulate a receptor and lead to a change in the function of the cell. Drugs can either have an agonist or antagonist property. We know what an agonist is, where the drug has both affinity and efficacy. An antagonist is a drug that has affinity for that receptor and can interact or bind with the receptor, but either does not produce a pharmacological response or it prevents any effect of an agonist. So like a beta blocker or an antihistamine, those are all antagonists. So again, this is, I'm sure, review for you guys, but so if a drug, or in this case a hormone, can come in and bind to this receptor like a lock and key, you're going to have that response from that hormone or drug A. We can also have a neurotransmitter. This neurotransmitter, in this case, as drug B comes in here, it's blocking the response from happening. So this is an antagonist, right? Some kind of a blocker, either an antihistamine or a I'm blanking, but a drug that blocks a reaction from occurring. Finally, drug C also this would be an agonist turning on this response. So, but there might be something else that's competing, whichever has the lower Km or the highest affinity is going to win that. So different responses we could see. We can see that there's some sort of endpoint that we're trying to go for, like a clinical response, maybe a surrogate for that we could be measuring. So these are different things that we might be measuring to determine if the drug is efficacious, right? We could be looking for a certain clinical response, like the lowering of a temperature or signs and symptoms resolving. We could be looking at a surrogate, so something that is going to change that is a surrogate for our response that we need. Maybe there's a biomarker. Maybe we're looking for a decrease in HbA1c or something like that. So there may be different things that we're looking for to measure our efficacy or the effect, because remember, this is all about concentration effect relationship. We are measuring sometimes against a placebo. We also may have to separate out any endogenous effects. So, for example, when we're lowering blood pressure, we're going to need to think about other things that could be changing the blood pressure that might be in addition or working against a drug. So we'd have to take that into effect, either placebo effect or endogenous compounds. There are two different types of effects that we're usually, or types of gradations of effect that we'll see. A graded response is, you know what? We're not gonna get into that. It's not that important. Okay, I'm gonna skip that for now. So we use models, just like we do in pharmacokinetics. We use models to try to predict what's going to happen with pharmacodynamics. So why do we model pharmacodynamics? Because we need to understand that concentration-response relationship so that we can predict it, right? It will help us to know what dose and dosing regimen, I put dose rate, but dosing regimen, what dosing regimen we should do to give to achieve a certain effect and avoid toxicity, and therefore we can link kinetics with the effect. So if we can model pharmacodynamics and link that with our model for kinetics, we have the whole thing solved. We know exactly how much drug we should give per time to get a certain effect. It also will help us increase unusual relationships that are not easily understood. So, for example, we have here 3 different concentration response relationships. So here's our concentration, increasing our concentration. This is in milligrams per liter. And here's our increasing effect. So this is going to be our independent variable, and here is our dependent variable. So the effect depends on the concentration, doesn't it? The concentration does not determine the effect. Or, I'm sorry, the concentration determines the effect. The effect does not determine the concentration. So if we start out, I'm going to start out with the pink one. So because it's the middle one. So as we increase our concentration, we see our effect increases pretty dramatically. It's a pretty steep slope. And then once we get up here, this starts to flatten out. So we have an increase in our effect as we increase our concentration, then that starts to slow, and we don't see much change in our effect as we increase our concentration. So that has what we call an N of 1, which is a slope factor. Let's compare that to our navy one here that I'm going to make green. So what we see with this one is a dramatic increase in concentration, even with tiny little bit of increase in concentration. And then this starts to flatten out. So we're seeing very little change, even though we're increasing our concentration dramatically here. There's really no change in effect, or very little change in effect between 0.2 here and 1 milligram per liter. It's hardly changing at all. And then our final one, that has an N of 0.3, so it's less than that N of 1. Finally, if we have an N of 3, so it's bigger than either, it's the biggest slope factor. What we see here is, again, not a very rapid increase in effect as we increase our concentration, and then flattens out to pretty much nothing. So we go from 0 to almost 100% in a very short amount of time. This is kind of called an on-off effect. So going from a concentration of, let's say, 0.01 maybe. Well, that would be 1. Yeah, something like that. To 0.3, and we have our whole range. So there isn't much difference between 0.01 milligrams per liter and 0.3 milligrams per liter. We've gone from 0 to 100%. So this is a very small concentration range. So this is considered to be like an on-off effect. So very small difference between totally on and totally off. We see that the larger the slope value gets. So this is using models. I should have said, yeah, we're now using models. How do we determine the potency of a drug? The potency of a drug is really all about how much, let me erase this, how much drug it takes, or the attraction between the receptor and the drug. So the lower the amount of drug it takes to get 50% of the effect is our potency. So the lower concentration of drug we need to get 50% of effect is our highest potency. Let's think about that for a minute. So this is just like any affinity constant. So what's the concentration where we're at 50% effect? So our 50% effect line is here, let's say. I'm not doing a very good job of drawing. Let me try that again. Whoopsie. Whoopsie. So, oopsie. Sorry, I'm having all kinds of problems here. Alright, we're going to try this one more time. Apologize here. Alright, back to where we were. Alright, so if we draw a line across here at the 50, so this is 50% of our effect. At 50% of our effect, we can see that this concentration, this is going to be our most potent drug, isn't it? Because it takes the smallest concentration to reach half the effect. So pink is going to be the most potent. And this yellow guy here is going to be our least potent of these three, right? Because here it takes about 1 milligram per liter to get to 50%, and this is like at 0.1 maybe. I'm sorry, 0.01 or some 0.1 milligrams per liter. So this pink one is the most potent, followed by the navy, followed by the yellow. Okay, that's going to be it for this. The next video we're going to get into the different models that we can see, and we're going to be starting with the most complex model, which is the sigmoid Emax model. Then this is the little less complex, and then we're going to finish off with a linear model. So these are all pharmacodynamic models that can describe the relationship between the concentrations we achieve and the effect we see. So it's going to be concentration, effect, right? And what kind of relationship we're seeing here. So at any particular concentration, what's the effect going to be? Okay, so we'll see you in the next video.